Alright, so this is our next video on integration for Math 1560, Calculus 1 at U of L for fall 2017. In the previous video we introduced the idea of estimating the area under a curve by using rectangles to approximate the true area. So now we're going to develop the formalism that is needed to kind of turn these ideas into equations that we can work with. So just to remind you where we're at, we have a function between two values a and b, so we've got the graph, say y equals f of x from a up to b, and we want to calculate this area. And the way we do this is we take the big interval from a to b, we divide it up into a number of smaller intervals, and in each one of these intervals we choose a point somewhere in the interval and we calculate the value of the function at that point. Okay, like so. And then what we do is, for each one of these subintervals and for each one of the points, we construct a rectangle whose base is that subinterval and whose height is given by the value of the function. So our first rectangle is here, our second rectangle is here, our third rectangle is here, the fourth one is here, and the fifth one is here. And you can see that if we add up the area of those rectangles, these 5 rectangles in this case, it's going to give us a reasonable approximation to the area, right? The area of those rectangles tracks the area under that curve fairly well. Of course, the curve that I drew in this case doesn't, it doesn't change. There's not a lot of variation in the y values between a and b. It's not constant, but we don't see any rapid changes in y value. A function that is more rapidly changing might not work so well, right? If I had a function where the graph kind of went like this, and I tried the same sort of thing with rectangles, I might be kind of here, and then the next point I'm down here, right? And then the next one maybe I'm up there, and then I'm here, and so I might end up missing piece. I might end up being quite a bit over or quite a bit under, depending on how much the function changes and how many rectangles I use. But the idea is still the same. We can approximate using these rectangles. So the first step in setting up these approximations is going to be to actually say precisely what we mean by dividing the original interval AB into subintervals. This division into subintervals is called a partition. So the way we do it, we start with our interval from A to B, and we choose a bunch of points between A and B, right? So our interval looks like this, right? Here's A, here's B, and we just start choosing points, x1, x2, x3, and so on. Right? And obviously the number of points is going to affect the spacing, right? If we only choose a few points, we're going to be fairly widely spaced. The subintervals will be reasonably large. If we try to put a lot of points in there, the length of each one of these intervals is going to need to be smaller. So we break things up into intervals, right? So we get our first interval. If we set a equal to x naught, our first interval is here from x naught to x1. Our second interval goes up to x2. So this is sort of interval 1, interval 2, interval 3 goes up to x3, right? In general, interval I, right, this would be interval I, or the ith subinterval if you like, goes up to xi, right? And so then the final one, interval n, goes up to xn, where xn is equal to b. So we break up into these intervals, right? And the width of each interval, of course, the length of an interval is just given by the right endpoint minus the left endpoint. So we have this formula that you see here, right? So delta xi is just left minus right, and in general, there's no reason that these intervals have to be of the same length, so it might be that delta xi is different for each I. We're going to see that most of the time we actually choose them to be the same length. When we do choose them to be the same length, we have what's called a uniform partition. So in a uniform partition, we decide how many pieces we want. So n is the number of pieces that we want to have. And we take our interval and we divide it up into n equal pieces. And of course, if we have n equal pieces that each have the same length, the length of, so the b minus a, right, that's just the length of the original interval. So that's the length of the interval from a to b. And we're going to divide it into n pieces, so each piece will have length given by b minus a divided by n, right? So this delta x is it's the length of each one of my subintervals. And once you make this choice, well, you actually now know what all of your partition points have to be, right? X naught, as always, is the left endpoint, is a. And now we know that, well, delta x1, right, is x1 minus x naught. Well, that means that if I solve this for x1 is going to be x naught plus delta x1, but delta x1 is just delta x, so I get that x1 is a plus delta x, right? x2, same sort of argument says that x2 should be x1 plus delta x, but of course x1 is x naught plus delta x, so this becomes x naught plus delta x plus delta x, which is x naught plus 2 delta x. So I get a plus 2 delta x, and you can probably guess how this is going to go, right? If I go to x3, I add another delta x, so I get to 3 delta x. x3 is going to be a plus 3 delta x, and so on. So after I steps xi is going to be a plus I times delta x, and so on down to the last one, which will be a plus n times delta x, right? So what this looks like if we actually put delta x in, x1 is going to be a plus b minus a over n. x2 is going to be a plus 2 times b minus a over n, and so on. So xi looks like this. It looks like a plus I times b minus a over n. And notice in particular that for xn I get a plus n times b minus a over n, and n's cancel, so that's a plus b minus a. I get b. I end up at the right endpoint, which is exactly where I expect to get, right? So the main takeaway here is that this formula here tells you how to generate each of the points in your uniform partition. So let's see how this looks in an example. If we go with the partition, we go with the interval from 0 to 4, right? So a equals 0, b equals 4, so b minus a is 4. Our delta x is then 4 over n, right? So in part A, well, delta x is just 4 over 4 is 1, right? So we get x naught is 0, x1 is going to be 1 plus delta x, that's 1 plus 1, I get 2, right? x2, I get 1 plus 2 delta x, so 1 plus 2 times 1, I get 3, and so on. x3 is going to be equal to, oh, sorry, I realized what I did wrong here. I knew I was getting too far ahead. X naught is 0, so x1, sorry, is 0 plus delta x, so 0 plus 1, which is 1. x2, I do now x1 plus delta x, so 1 plus delta x, 1 plus 1 is 2, x3 I get 2 plus 1, I get 3. x4, I do 3 plus 1 more, I get 4. Okay, so that's pretty clear what's going on. We start at 0, we end at 4, and our pieces are, we're dividing at 1, 2, 3, and 4. We get our equal pieces. If we do 8 subintervals, well, then our delta x is 4 over 8. We get 1/2. And this time I'll go a little bit more quickly. X naught is 0. x1, we add delta x1, so we add a half, so we get 1/2. x2, we add half again, so we get to 1. x3, we add half one more time, gets us to 3 over 2. x4, we add half again. Now we're at 2, right? 4 over 2 gives me, oops, I want to write 4 for some reason. x4 is 2. x5 is 2.5, that's 5 over 2. x6 is 6 over 2, that's 3. x7 is 7 over 2, and then of course x8 is 8 over 2, which is 4, which is our right endpoint. So we get where we're supposed to go. If we were doing this in general, n subintervals with n unspecified, well then delta x is simply 4 over n. We would have x naught is still 0. x1 is going to be 4 over n. x2 is going to be 8 over n. And well, this time, because we didn't say how far we're going to go, we can just say, well, what does a general term look like? xi, after I times, we're doing I times delta x, so it's 4 times I over n, all the way down to xn, which will be 4 times n over n, which is just 4. Okay, so that's how you construct a uniform partition. In the next videos, we'll see how to use these uniform partitions to build what are called Riemann sums, and Riemann sums are exactly these sums of areas of rectangles that we use to approximate the area under a curve.